Good afternoon, ladies and gentlemen. I am Shaurya Sood, and in next 20 minutes or so, I shall be presenting work in progress on slow rate HTTP attack detection with behavioral parameters. For ease of understanding, the presentation is divided into following heads for about 20 minutes or so. Introduction. DOS and DDoS pose a threat to safety of network services and applications. They are growing in scale and variety, and simple detection methods are easy to evade. HTTP, SIP, DHCP, DNS, and NTP are example targets. The modus operandi of an adversary is to cripple the server by prolonging the connection duration to exhaust the connection pool. Application layer denial of services reduce resource requirement for an attacker. That's why they are much more liked by an attacker. And it also enhances the stealthiness of the attack. In our detection approach, 4 parameters, 3 measured at the server and 1 at the designated client are used. And finally, we tested it on the live college server. Literature survey. Here are some papers from 2014 and 2015 pertaining to our work. Some more existing work from 2017. Some more work from 2017 pertaining to denial of services and especially to HTTP distributed denial of services. Here are some papers from 2018 that we referred prior to commencement on our work on slow low-res attack detection. And finally, some recent work on denial of services from the current year. Now let us understand the working of slow low-res attack. In our example here, the blue server on the right is the benign web server and the maroon laptop on the left is an attacker. Now let's understand how easy it is for a slow low-res attacker to take down the Apache web server. The attacker connects with the server on port 80, sends a GET HTTP request along with the version, sets the host name, and then sends a header and waits for T seconds. Before the server decides that the connection is timed out, the attacker again sends another header but does not send another CRLF, which means the connection is complete. This will render the server from giving the response back to the attacker. Just imagine if multiple such requests are forwarded to the server, the connection pool at the server will be crippled, which means the server will not be able to reply to the legitimate requests. And this happens because the server gets overloaded because of such slow requests. And the only resource which is required by the attacker is a small little laptop in order to carry out the denial of services attack on the web server. This can be done in a distributed fashion also. Summary of mitigation methods. Web servers, in order to mitigate the slow low-res threat, implement different modules. For example, core module buffers the HTTP requests and forwards only the complete request to the server. This guards the server from the attack, although it requires enough space in kernel. Anti-low-res and limit IPCon modules limit the complete or incomplete HTTP requests per IP address and thereby guarding the server. Mod request timeout enforces the sender to send the entire request in a predefined amount of time, and by this way it guards the server from the attack. Some servers also rely on overlay-based mitigation methods. These methods work on the principle of filtering and load balancing. These are commercial solutions which are already available, provided by Cloudflare and Akamai's Kona. Some SDN-based methods do not provide end-to-end encryption. The idea of filters is that we set them away from the servers. The dedicated servers which carry out filtering forward only legitimate requests to the server, thereby guarding against the slow loris attack. Load balancing also works in the similar fashion. These servers also carry out client identification before forwarding the request, thereby guarding against the malicious requests. In the another set of mitigation techniques which follow traffic profile and feature based detection, we have server profile based on traffic and system resources. HTTP server profile calculate the Hellinger distance between historic profile and the test interval in order to label that particular interval as malicious or benign. These detections are based on threshold. However, single threshold based techniques are easily evaded. Some machine learning methods for detection have also been provided in various literature survey that we have gone through. However, the resultant is the combination of features and characteristics are required to detect these attacks because single threshold based methods are easily evaded. Motivation for work. HTTP is a popular protocol. Every person who has surfed the internet is aware about HTTP. Surface area of attack pertaining to this protocol is well known to the attacker. Application layer denial of services attacks per se targets the working of HTTP protocol in order to carry out the exploit. As we have seen from the literature review, the single threshold based techniques are not very successful to guard against such attacks. Hence, there is a requirement of detection techniques which is based on the combination of features and characteristics. Features are the physical measure, for example, packet size is a physical measure, and characteristics is a behavior pattern which is seen during the attack. For example, while the attack is in play, the response time increases. This is a behavior pattern or a characteristic. With this as a background, we propose the following method. By carefully studying the normal and slow loris attack instances of a web server, we identify following four features and characteristics as attack indicators. The key to detecting attacks is identifying parameters which are relevant and can differentiate normal and attack scenarios. Incomplete requests. An incomplete request is a packet that is ending in incorrect terminating sequence which otherwise is required by the HTTP protocol. When the server is under attack, the number of incomplete requests obviously increase. Such incomplete requests are otherwise not seen in regular or normal requests from clients. Thus, we chose this as our first attack indicator. Response time. This is the time difference between a request made by a client to receiving a response. When a web server is experiencing slow rate attack, all the available connections with the server are utilized and hence it is likely that legitimate requests are not honored or experience very slow response. It is worth noting that response time is dependent on load the server is experiencing and the state of the network. If the load on the server is more, the response may be slower. Also, if the network is experiencing congestion, then also there will be large delays. Thus, response time is a good indicator but insufficient on its own to detect attacks. Number of response messages from the server. With increase in number of incomplete requests, the server response slow down and hence will send less number of bytes or responses, otherwise it is sending normally. Number of context switches. A context switch will happen when the operating system switches from one process to another. This is different from an interrupt. Interrupt is a service request and the execution will resume from the state where it was left after servicing the interrupt. In case of slow loris attack,
The number of context switches are likely to increase as new connections are made in short span of time. In order to understand the efficiency and effectiveness of these features, we carried out a small experiment for about 10 minutes and we mounted the attack for 2 times for short durations of time. The results will be discussed in subsequent slides.
Let us now understand how incomplete requests are detected. We implement a function to check a packet and we have a complete connection string given in binary as double carriage return line feed. We check if the packet is ending in the correct sequence, that is double carriage return line feed, then it is a complete request. However, if the packet is ending with only one sequence of carriage return line feed, then it is considered as an incomplete packet or an incomplete request. We also term it as slow low risk packet. In the last else condition, if not these two conditions are satisfied, then it is some other packet. In this graph, we see the blue bars are saying how many requests which are complete are seen in a time window. The bars in the maroon color or red color are showing the existence of incomplete requests. Now, this existence of incomplete requests is happening only in the time duration in which this slow low risk attack was mounted on a server.
Response time is a time taken by the server to respond to the legitimate requests. Hence, response time cannot be measured at the server. Therefore, we have to establish a set of clients with specialized scripts in order to measure the response time which is initiated from a client end. We have two options. Either we write a Python script, the one which is in front of you, or we use the curl command in order to measure the round trip time between the requests. Here, when we plot the response time on a graph for our quick experiment of 10 minutes, we see that there are two spikes in the maroon bar chart representing response time increase. These are exactly those times when the attack was mounted for a short duration on the server.
Server response messages. This parameter is measured at the server. Here is the code snippet which helps find out IP or IPv6 protocol from the given frame. Thereafter, the source IP is compared with the local IP of the server. If they both match, then we consider that it's a response message initiated by the server for a client. Here is the graph of responses from the server. We can see in both time windows when the slow low risk attack was mounted, there is a significant dip in the response messages. That means when the slow low risk attack is initiated on a server, in that time duration, the server response messages see a significant dip. Context switches is a parameter which is measured at server. Here is the code snippet, and there are two types of context switches, voluntary and non-voluntary. In our code, we are using psutil library to calculate the context switches. Here is the graph when we plot on the timeline. We can see the voluntary context switches usually stay constant in a time window. However, in case of the slow low risk attack, the involuntary or non-voluntary context switches spike up when the attack is initiated. Detection of slow HTTP attack algorithm. Here, all the parameters that we have discussed so far are taken and measured for a benign time window or a benign time period, based on which we calculate 5 thresholds: upper and lower threshold for incomplete requests, threshold for response time, response messages, and context switches. Now I draw the attention to the while loop, which is doing the entire process. The first if statement and last else statement is saying when the threshold is above a particular level, then we declare attack. And when the threshold is below a certain level, we say it's a normal operation. However, in case some attacker is trying to fool the system by working below the threshold level, then the other parameters come into play and decide whether that time window is benign or malicious. I draw the attention to the else if statement that we have written, where we are saying the incomplete is greater than equal to incomplete request 2, that is the second threshold, and it is less than incomplete threshold 1, which means it is between the above and below thresholds. Then we take out the combinations of response time, response message and context switches, and based on the condition which is nested inside, we decide whether the window is benign or is malicious. The experiment setup.
In this experiment setup, we have an Apache web server, cluster of 3 clients running Ubuntu operating system and 2 attacker terminals with the Kali Linux. At the server, we installed Wireshark in order to analyze the incoming packets, and the same has been implemented using Scapy library in Python. The response measurement clients are running JMeter in order to provide a dummy traffic to the server, curl script which measures the round trip time, and the same script has been implemented using Python 3. The attackers are running the slow loris attack scripts available from the open source. Once the experiment was completed and the results were satisfactory, we extrapolated this attack on a live web server for the better results. For the larger experiment, this time the experiment was run for about 7 hours. Now let us discuss the results of these both experiments in subsequent sections.
So here is the way we calculate and set the thresholds. We run the experiment for about 2 hours to find out the threshold values from the average of all parameters. We can see the threshold number 1 is initially not applicable because in the experiments we see that there is no availability of incomplete requests in the benign traffic. Now we take an intuitive value of 100 incomplete requests as the threshold number 1. So anything beyond this would be termed as the attack window, or anything which is less than the average value of the second threshold, which is 4 in this case, and we increase it by 25% to make it 5. So anything which is less than 5 is clear-cut indicative of a benign window. Response time average value is 0.34 seconds. We add 25% and make it 0.4 seconds as a threshold. So anything which is beyond this time will help indicate that the window may be a malicious window. Similar way, the response messages average value in our conduct was 458, and the response messages, since they dip when the attack is mounted, we reduce 25% from this and come to the threshold value of 412. And same in the case of context switches, the average value is 25, so we add 25%, make it 30. Table number 2 shows the experiment results with our algorithm of detection. Here, the time window that we are taking is 15-second time window, and we can see the confusion matrix clear-cut says all normal windows were detected as normal and only 2 attack windows were detected as the normal. When we increase this time window, the algorithm efficiency increases. In the table number 3, we can see when the experiment was carried out with a 5-minute time window, the 100% efficiency of the algorithm was achieved. Now here is the sensitivity analysis of the algorithm. As and when the time window is less and it is less than 14 seconds, the efficiency is less than 100%. So when the time window was about 5 seconds, the efficiency is 37%. At 10 seconds, it increases to 69%. At 14th second, it goes to 99%. And thereafter, the algorithm efficiency after 16th second is 100%. So this was the experiment lab setup. Now we talk about the experiment which was carried out on the college server. Here Again, we used the same parameters and the same formula for thresholding. The first threshold was 100. In the second threshold, we found the count of 8, so we added 25%, made it 11. In the response time, again, we used the same formula, made the threshold from 0.24 to 0.3 seconds, which is 25% plus the average, and we calculated the number of response messages originated by the server were 1470. So we made a cut of 25%, get the threshold to 11 or 3, and the context switches, which was 10, we add 20% to it, made it 12. And then we see the performance in this experiment with the 15-second time window. We got all normal windows as normal windows and only 4 attack windows which were miscalculated by the algorithm and treated as the normal traffic. Here is the sensitivity analysis of this experiment. We can see when the time window was 5 seconds, the performance was 60%. At 10 seconds it increased, and beyond 25-30 seconds we can see the efficiency or the performance of the algorithm is 100%. With this, I come to the conclusion. Slow rate attack exploits the HTTP operation. It takes down the web servers with very fewer resources. That is why it is very liked by the attackers, or it is very popular with the attackers. Since single threshold methods are easily to evade, we have come up with a threshold of 4 parameters and the combination of 4 parameters which will help identify if the attack is working below a particular threshold. We carried out 2 experiments, testbed setup, which was based on our virtual machines, and then we carried out the experiment on the college live web server. The evaluation results showed good and detection performance in both the cases. With this,
Finally, the future plan of the work in progress. We are considering other parameters which can be helpful in the detection of slow low risk attack, and we would like to extrapolate our work for HTTP2 protocol.
with this, I come to the end of my presentation. Thank you very much. Should there be any questions, please ask.